Hello, everyone, and welcome back. Today, we're delving into a topic that touches us all, yet remains largely a mystery to many: the process of cremation. It's a choice made by countless families around the world, a final act of care and remembrance. But beyond the emotional and cultural significance, have you ever stopped to consider the profound scientific transformation that occurs within the cremation chamber? It's a process often misunderstood, sometimes even feared. But by peeling back the layers of misconception, we can uncover a truly fascinating and surprisingly intricate scientific journey. Understanding this process from a purely scientific standpoint can offer a unique perspective and, for many, a profound sense of peace. Let's begin by dispelling some common myths and setting the stage for what truly happens. A modern cremation chamber, often referred to as a retort, is far more sophisticated than just a super-hot oven. It's a meticulously engineered environment designed to facilitate the rapid and complete reduction of a body to its fundamental elements. We're talking about temperatures that soar between 1400 and 1800 degrees Fahrenheit, which, to put it in perspective, is hot enough to melt glass and significantly hotter than your average kitchen oven could ever achieve. The entire process for an average adult typically spans about 2 to 3.5 hours. However, it's crucial to understand that this isn't one continuous, undifferentiated burn. Rather, it's a carefully orchestrated sequence of distinct scientific stages, each playing a vital role in the transformation. Our journey begins with stage 1, initial heating. Imagine the body, respectfully enclosed within a combustible container, being introduced into the preheated chamber. For the first 10 to 20 minutes, as the ambient temperature inside the retort steadily climbs towards 600 degrees Fahrenheit, the container itself begins to char and emit smoke. During this initial phase, the body's internal temperature rises, but it's important to note that no actual burning of the tissue has yet occurred. This is a preparatory phase, gradually bringing the material up to the necessary temperature for the next, more dramatic stage. As the heat intensifies and surpasses the 600-degree mark, we transition into stage 2, ignition and primary combustion. This is where the most significant changes begin to unfold. The combustible container ignites, and very quickly thereafter, the body's soft tissues, the skin, subcutaneous fat, muscle tissue, and internal organs begin their combustion. A substantial amount of the body's inherent moisture, which constitutes about 60 to 70% of its total mass, rapidly evaporates, escaping as steam. One of the most intriguing aspects of this stage is the phenomenon of self-sustaining combustion. This occurs as the body's fat tissue liquefies and burns, releasing a significant amount of energy that actually helps to accelerate the overall process. This stage, typically lasting between 60 to 90 minutes, is characterized by the most visible flame and smoke as the organic matter is efficiently consumed. Now, let's address a common, often sensationalized misconception, frequently perpetuated by popular culture. Does the body sit up during cremation? The answer, unequivocally, is no. While the intense heat can cause muscle tension that results in slight limb movements or flexion, these are purely minor physical responses to the extreme thermal energy, not conscious actions. It's a natural, albeit sometimes unsettling, part of the scientific reaction to such high temperatures, and it's important to distinguish this from any dramatic, fictionalized portrayals. As the primary combustion phase gradually subsides, we transition into stage 3, complete combustion. During this critical period, the chamber meticulously maintains those intense temperatures, ranging from 1400 to 1800 degrees Fahrenheit. At this juncture, all soft tissue has been thoroughly consumed. What now remains are the resilient bone structures and any non-combustible materials, such as various metal implants. These could include hip replacements, knee prosthetics, or surgical pins, which are designed to withstand extreme conditions. The bones themselves undergo a fascinating chemical transformation known as calcification. In this process, their organic components, primarily collagen, burn away, leaving behind their robust mineral structure, which is predominantly calcium phosphate, also known as hydroxyapatite. This stage typically lasts between 30 to 60 minutes, with operators carefully monitoring the process to ensure thoroughness. Following this, we reach stage 4, final processing. The high temperatures are sustained, ensuring that the remaining bone structure becomes incredibly brittle and porous. The color of these fragments shifts to a chalky white or light gray, and due to their newfound fragility, small fragments may naturally break apart. This crucial phase, lasting approximately 15 to 30 minutes, is essential for preparing the bones for the subsequent steps, ensuring they are in the optimal state for final reduction. Once the cremation process within the chamber is complete and the retort has cooled sufficiently for safe handling, a period typically lasting 30 to 60 minutes, what remains is often referred to as ashes. However, this term is another common misconception. What's left is not the soft, powdery ash you might associate with a campfire. Instead, the remains are primarily bone fragments composed of calcium phosphate. These fragments are granular, ranging in color from grayish-white to beige, and for an average adult, they typically weigh between 4 and 8 pounds, which is roughly 3 to 5% of the living body weight. The exact color can vary based on factors like bone density, the individual's age, and even certain medications they may have taken. Before these cremated remains are returned to families, a few vital steps are undertaken. First, any non-combustible metal implants, such as hip or knee replacements, dental fillings, or surgical rods, are carefully removed. These metals, often made of titanium or stainless steel, do not melt at cremation temperatures. Interestingly, many crematories participate in specialized recycling programs for these medical metals, with the proceeds frequently donated to medical research or hospice charities, a surprising and impactful detail that often goes unnoticed. It's also important to note that pacemakers, which contain lithium batteries, must be removed before cremation, as they pose an explosion risk under high heat. After the removal of metals, the brittle bone fragments are transferred to a specialized machine known as a cremulator. This device, often likened to an industrial blender or pulverizer, is specifically designed to process the mineralized bone fragments. Using heavy metal balls or rotating blades, the cremulator grinds these fragments into the fine, uniform particles that families recognize as ashes. This mechanical reduction typically takes about 5 to 15 minutes, depending on the quantity and brittleness of the fragments, resulting in a consistent texture suitable for placement in an urn or scattering. Now, let's briefly touch upon the historical context of cremation. While modern cremation, as we know it, gained traction in the late 19th century, the practice itself dates back tens of thousands of years, with evidence found in ancient civilizations across the globe. It was a common practice in ancient Greece and Rome, often associated with beliefs about the soul's release. However, with the rise of Christianity in the West, burial became the predominant practice due to beliefs in bodily resurrection. The modern revival of cremation was spurred by advancements in hygiene and technology, notably showcased at the 1873 Vienna World's Fair with Professor Ludovico Brunetti's reliable cremation furnace. The first modern crematory in the United States was established in 1876 by Dr. Francis Lemoyne, marking a significant shift in funerary practices. Beyond the immediate process, there's also the question of environmental impact. When comparing cremation to traditional burial, both have their ecological footprints. Cremation, for instance, releases approximately 400 kilograms of carbon dioxide per body, roughly equivalent to a 500-mile car trip. However, modern crematories are equipped with advanced filtration systems to minimize emissions, including mercury from dental amalgams. Traditional burial, while seemingly more natural, involves land use, the use of embalming chemicals like formaldehyde, and often non-biodegradable caskets and vaults. The choice between the two often comes down to personal preference, cultural beliefs, and a consideration of these varying environmental factors. So, the journey inside the cremation chamber is a profound scientific transformation, a carefully managed process that reduces the physical form to its most basic mineral components. From the initial heating and the intricate chemical reactions of combustion to the final processing of bone fragments, it's a controlled, respectful, and surprisingly intricate scientific endeavor. Understanding these scientific realities can demystify a topic often surrounded by discomfort, replacing it with knowledge and, for many, a deeper sense of peace. It's a testament to how science helps us navigate even the most sensitive moments of life and loss, offering clarity and understanding in times of profound change. Thank you for joining us on this scientific breakdown. We hope this exploration has shed some light on a complex topic and provided you with a deeper appreciation for the science behind cremation. If you found this informative and thought-provoking, please consider liking this video and subscribing to our channel for more fascinating insights into the world around us. We'd love to hear your thoughts and any other scientific processes you'd like us to explore in the comments below.